Graphene is one of the most extraordinary materials humanity has ever discovered. Imagine a sheet of carbon atoms arranged in a honeycomb lattice so thin that it is only one atom thick, yet so strong it could theoretically stop a bullet. This is graphene, a substance lighter than paper, more conductive than copper, stronger than steel, and almost transparent to the eye. When scientists first isolated graphene in 2004 using little more than Scotch tape and graphite, it seemed like an interesting laboratory novelty. But soon the implications became clear. Graphene isn't just a new material. It may be the foundation for entire civilizations, enabling structures and machines that previously belonged only to the imagination of science fiction. Today, we'll explore what it means to design skyscrapers and bridges out of graphene, what challenges lie ahead, what breakthroughs are required, and how this atom-thin wonder material could reshape the built environment of tomorrow. To understand the future, we first need to appreciate the physics of graphene. Carbon, as an element, is remarkably versatile. In diamond, each atom bonds with 4 others in a tetrahedral shape, producing an ultra-hard crystal. In graphite, carbon atoms arrange in layers that slide over one another, producing the familiar softness of pencil lead. But in graphene, carbon atoms bond in a 2-dimensional hexagonal sheet, forming an elegant honeycomb that provides an unusual blend of properties. The tensile strength is over 130 times greater than steel, yet graphene weighs virtually nothing. Its electrical conductivity outperforms copper, while its thermal conductivity is nearly unmatched. This means that graphene is not just strong, but smart. It can carry electricity, manage heat, and interact with light in unique ways, giving architects and engineers a multi-dimensional tool for construction. Now imagine applying these properties to megastructures. Today's tallest skyscrapers are limited by steel and concrete. As buildings rise, their weight increases dramatically, placing enormous pressure on lower floors. Wind shear becomes a destabilizing force, requiring thicker and more rigid foundations. At some point, materials simply fail under the stress. But graphene offers a pathway around these constraints. A skyscraper made of graphene composites could rise kilometers into the sky, with walls thinner than glass yet stronger than reinforced steel. Its weight could be drastically reduced compared to conventional towers, enabling foundations that are less invasive to the earth beneath. These structures could become so tall they pierce the stratosphere, acting as platforms for orbital elevators, communication hubs, or even space tourism. Bridges, too, would be revolutionized. Current suspension bridges span kilometers at most, with cables made of steel wires under constant tension. Graphene-based cables would not only be lighter but exponentially stronger. Imagine a bridge spanning entire seas, connecting continents with elegant arcs of atom-thin strength. Bridges that today are impossible because of wind pressure, water currents, or seismic activity could become practical, as graphene structures would flex, bend, and adapt rather than collapse. These structures wouldn't just be feats of architecture. They would be instruments of global connectivity, uniting cultures and economies with direct pathways across oceans. But before we leap into science fiction, we need to ground ourselves in the challenges. The biggest barrier today is manufacturing. Graphene, in the laboratory, is miraculous. But creating graphene at industrial scale is incredibly difficult. Producing sheets of pure graphene large enough to cover buildings or suspension cables is still beyond our current reach. Most graphene today is synthesized in small flakes, powders, or narrow films. These are useful for electronics, coatings, and sensors, but not yet for megastructures. For graphene skyscrapers to rise, we need breakthroughs in large-scale synthesis, where sheets extend for kilometers without defects. Even a single imperfection in the lattice could compromise its strength. Imagine a scratch on a pane of glass, scale that up, and the entire megastructure could be at risk. So, the first step toward graphene megastructures is mastering perfect, defect-free production. There's also the challenge of integration. Pure graphene sheets are too thin to handle as bulk material. Engineers must design composites, materials that mix graphene with polymers, metals, or other carbon structures. Think of graphene acting like steel rebar in reinforced concrete, except at the atomic level. Such composites could be engineered to combine graphene's strength with flexibility, allowing skyscrapers to sway in the wind or bridges to flex under load without breaking. But how do you attach one graphene sheet to another? How do you bind them into something larger than microscopic scale? These are the unanswered engineering questions of our age, and entire research fields are dedicated to solving them. Yet despite the obstacles, progress is happening. Already, graphene-enhanced concrete is being tested, promising higher strength and less environmental impact. Graphene composites are used in aircraft for lighter wings and stronger fuselages. Even sports equipment like tennis rackets and bicycle frames use graphene for improved performance. Each of these small steps points toward a larger future, where entire skyscrapers and bridges may be woven from graphene's atom-thin fabric. Imagine walking across a bridge where the cables are thinner than your wrist, yet strong enough to hold millions of tons of traffic. Imagine entering a skyscraper where walls feel impossibly light but remain immune to earthquakes. This is not fantasy, it is a material trajectory, where today's laboratory experiments scale up to tomorrow's infrastructure. The cultural impact of graphene megastructures would be profound. Architecture has always been a reflection of power and possibility. The pyramids of Egypt symbolized eternity. The cathedrals of Europe embodied spiritual devotion. The skyscrapers of the 20th century symbolized economic ambition. But graphene towers rising into the clouds would represent something different, a fusion of science, technology, and human imagination. They would not just be places to live or work. They would be monuments to a species that learned to re-engineer the very fabric of matter to transcend gravity, time, and limitation. They would be our cathedrals of carbon, our monuments of the atom. Beyond aesthetics, graphene megastructures could reshape how we live. With their weight savings and strength, they could incorporate renewable energy systems seamlessly. Entire skyscrapers could double as vertical solar farms, their outer layers coated with graphene-based solar cells. Bridges could harvest wind energy as cars pass, turning infrastructure into power plants. Graphene's transparency and conductivity could enable walls that function as both windows and displays, making every surface interactive. Your office window could transform into a screen, or your apartment wall could project immersive environments, powered by the building itself. The line between architecture and electronics would blur, as graphene integrates computation, communication, and construction into a seamless whole. We must also consider the societal implications. Who will control the production of graphene at industrial scale? Will megastructures be symbols of unity, shared among nations, or symbols of inequality, accessible only to the wealthiest cities? The skyscraper has always been an emblem of economic disparity, rising above neighborhoods often struggling below. If graphene structures rise only in certain parts of the world, they could widen the gap between developed and developing nations. Conversely, if graphene manufacturing becomes affordable and widespread, it could enable infrastructure revolutions in places that need it most: stronger, safer, and cheaper buildings for billions of people. The future of graphene is not just a scientific question. It is a political, economic, and ethical one. And then, of course, there are the visionary possibilities. Imagine a world where graphene allows us to construct floating cities tethered by lightweight megastructures, immune to rising sea levels. Imagine space elevators stretching from Earth to orbit, their graphene cables extending into the heavens, enabling cheap and frequent access to space. Imagine orbital rings circling the planet, built from graphene composites, acting as highways between continents. These are not impossible, they are the logical extension of material progress. Where steel enabled skyscrapers in the 20th century, graphene may enable planetary-scale architecture in the 21st and 22nd. But every future comes with risks. What if graphene becomes weaponized? Super strong, nearly invisible materials could create armors and weapons unlike anything seen before. What if economic monopolies lock down access to graphene, preventing its potential from reaching the world? What if structures built from graphene fail due to unforeseen weaknesses at scale, causing catastrophic collapse? As with all powerful technologies, the path forward requires careful planning, regulation, and shared vision. In education, graphene megastructures will also inspire. Young students learning about atoms, lattices, and materials will see their abstract lessons manifest as living skyscrapers and bridges. Universities will train architects who think not in terms of steel beams and concrete blocks but in atomic layers and quantum effects. This could inspire an entirely new discipline, atomic architecture, where buildings are designed from the molecular scale upward. Just as nanotechnology has transformed medicine, it could soon transform the built environment. The narrative of graphene is still being written. Right now, we stand at the threshold, holding pieces of this wonder material in laboratories and prototypes. But the horizon is vast. 6 decades from now, cities may rise on graphene foundations. Oceans may be crossed by graphene arcs. Humanity may look back on this century as the moment we shifted from stone, steel, and glass to atom-thin carbon sheets as the foundation of civilization. Just as the Bronze Age and Iron Age defined epochs of history, we may soon speak of the Graphene Age, an era where construction, energy, and electronics merged into a single fabric of possibility. The story of graphene megastructures is more than science. It is the story of humanity's imagination materialized. When skyscrapers of atom-thin carbon cast shadows across the Earth, when bridges woven from molecular honeycombs stretch across seas, we will know that we have learned to engineer not just with matter, but with dreams. And in those structures, standing light yet eternal, we will see not only the strength of carbon, but the strength of the human spirit that dared to think beyond the limits of stone and steel. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.